Welcome to the Exponential Models Masterclass for SAT Math Data Analysis. In this lesson, you'll master growth, decay, and predicting change using multipliers. If you can spot the multiplier, you can solve these problems quickly. Let's begin. Next, let's lock in the core idea behind exponential models. Exponential models happen when the change is a constant percent. That means you're not adding the same amount each step, you're multiplying by the same factor each step. So here's the key sentence. When the percent is constant, the multiplier is constant. If it's growth, your multiplier is greater than 1. For example, a 5% increase each step means you multiply by 1.05 each time. If it's decay, your multiplier is between 0 and 1. For example, a 20% decrease each step means you multiply by 0.8 each time. That's why the key form looks like this. Value equals start times multiplier to the power of time. In other words, you begin at a starting value, then you apply the same multiplier again and again, and the exponent tells you how many steps you've taken. So on every SAT question, don't rush to memorize formulas first. Instead, identify 3 things: the start value, the multiplier, and the time step, meaning what one step represents in the context. Finally, remember this: your predictions are most reliable inside the data range. Once you go outside the range, the pattern can change, and the model can break. So the SAT habit is: focus on what the situation is doing, percent change right pointing arrow multiplier right pointing arrow repeated steps, and the exponential model will feel automatic. Growth or decay, how do you tell? The multiplier tells you which one it is. If the multiplier is greater than 1, the value increases each step, so that's growth. If the multiplier is between 0 and 1, the value shrinks each step, so that's decay. Now, on the SAT, the key move is turning a percent into a multiplier. If something changes by p% each step, first convert that percent to a decimal. That decimal rate is r, and r equals p over 100. So for an increase, the multiplier is 1 plus r. For a decrease, the multiplier is 1 minus r. That matches the formulas on the slide: 1 plus p over 100, or 1 minus p over 100. That's why this growth example can use a multiplier like 1.06, and this decay example can use a multiplier like 0.85. So remember, greater than 1 means growth, between 0 and 1 means decay, and percent change becomes a multiplier you apply every step. Start value, also called the initial value, is where an exponential model begins. It's simply the value at step n equals 0, before any repeated percent change happens. In the model, value equals start times multiplier to the power n. The start is the number you get when you plug in n equals 0. That's why the start value is the anchor for everything you do next. If a problem gives you a table, the start value is the value at the first step shown, the earliest entry, before the pattern repeats. If a problem gives you a graph, look at n equals 0 on the horizontal axis, and read the y value there. That y value is the start value. In this picture, the point labeled start, n equals 0 is the starting value, and then each step multiplies by the same factor, like times 1.06. So here's the habit for SAT questions. Before you calculate anything, label the start value first. The multiplier is the number you multiply by each step. It's the fastest way to handle exponential change on the SAT. Start with a percent change, and turn it into a multiplier. If something increases by p% each step, convert p% to a decimal by dividing by 100. Then the multiplier is 1 plus p over 100. If something decreases by p% each step, you still divide p by 100, and the multiplier is 1 minus p over 100. For example, an increase of 6% means you multiply by 1.06. A decrease of 15% means you multiply by 0.85. Once you have the multiplier, the rest is consistent. Each step means you multiply by that same number again and again. So before you do any powers or calculations, lock in the multiplier first. The number of steps, n, is one of the most common SAT mistakes in exponential models, because n is not the final value, and it's not the percent. N simply counts how many times you apply the multiplier. Start at n equals 0. That's the start value. When you move forward one step to n equals 1, you multiply by the multiplier once. Move to n equals 2, you've multiplied twice. And by the time you reach n equals 3, you've multiplied 3 times. So notice the key idea. From n equals 0 to n equals 3 is 3 steps, not 4. It's 3 equal jumps forward, and each jump is one multiplication. That's why you should always pause and read the question carefully. Does it say, after 3 steps, after 3 years, or, at time n equals 3? Once you lock in n correctly, the rest of the calculation becomes straightforward. Now let's put everything together. Every exponential model question on the SAT becomes easier when you identify 3 things first: the start value, the multiplier, and n, the number of steps. Start value is the value at n equals 0, the beginning of the process. The multiplier is the percent change written as one number you multiply each step. 1 plus p over 100 for an increase, or 1 minus p over 100 for a decrease. And n is simply how many times you apply that multiplication. Once those 3 pieces are labeled, the model is automatic. Value equals start times multiplier to the power n. So don't rush into calculations. On the SAT, the fastest path is to pause, label start, multiplier, and n, and then plug them into the formula. First, identify the start value, the value at n equals 0. Second, identify the multiplier. If it's an increase, it's 1 plus p over 100. If it's a decrease, it's 1 minus p over 100. Third, identify n, the number of steps, how many times you multiply. If you label those 3 pieces first, the equation becomes automatic. Value equals start times multiplier to the power n. Now we're ready for the part that actually raises your score: practice. I'll give you a few SAT-style questions. Try each one on your own first. You can pause if you'd like, and then we'll walk through the solution step by step, focusing on how to choose start, multiplier, and n correctly. Let's begin. Here's a beginner practice problem for exponential growth. A population starts at 500 and increases by 6% each year. Your goal is to find the population after 3 years. Before you calculate, use the checklist. Start value is 500 at n equals 0. 6% increase means the multiplier is 1.06. And 3 years means 3 steps, so n equals 3. Pause here if you want to try it first. When you're ready, we'll build the model and compute it step by step. Let's solve it. Start value is 500, because that's the value at n equals 0. Since it increases by 6% each year, the multiplier is 1 plus 0.06, which is 1.06. And, after 3 years, means 3 equal steps, so n equals 3. So the model is, value equals 500 times 1.06 to the power n. Now plug in n equals 3, 500 times 1.06 cubed. 1.06 times 1.06 is about 1.1236. Multiply by 1.06 again to get about 1.191. Now multiply by 500. That's about 595.5. So the population is about 596 after 3 years. The main SAT habit is this: label start, multiplier, and n first, then do the math. Next, a decay example. A device costs $200 and loses 15% of its value each month. Find the value after 2 months. Use the checklist. Start is 200 at n equals 0. 15% decrease means the multiplier is 1 minus 0.15, which is 0.85. 2 months means 2 steps. Pause if you want to try it. Then we'll solve it together. Start is 200. A 15% decrease means the multiplier is 1 minus 15%, so it's 0.85. 2 months means n equals 2. So compute 200 times 0.85 squared. 0.85 times 0.85 is 0.7225. Now multiply by 200, which gives 144.5. Notice the quick check. Since the multiplier is less than 1, the value must go down. That helps you catch mistakes fast. Here's one more beginner problem, focused on n. The balance starts at 50 and decreases by 20% each week. Find the balance after 4 weeks. Start is 50. 20% decrease means the multiplier is 1 minus 0.2, so it's 0.8. And 4 weeks means 4 steps, so n equals 4. Pause if you want to solve it first. Multiplier is 0.8 and n is 4. So we compute 50 times 0.8 to the fourth. A quick way is to square first. 0.8 squared is 0.64. Then square again to get the fourth power. 0.64 times 0.64 is 0.4096. Now multiply by 50. That's about 20.48. So after 4 weeks, the balance is about $20. This is why n matters so much. Each step is one multiplication. Now intermediate practice. We're given a table. At n equals 0, the value is 100. At n equals 2, the value is 121. The question asks for the multiplier per step. So we need the number that, when multiplied twice, turns 100 into 121. Pause here and try it. Then we'll solve it. From n equals 0 to n equals 2 is 2 steps. So the model is 100 times multiplier squared equals 121. Divide both sides by 100. Multiplier squared equals 1.21. Now ask, what number squared gives 1.21? 1.1 times 1.1 is 1.21. So the multiplier is 1.1. That also means it's growth, because the multiplier is greater than 1. This is a common SAT move. When the table jumps by 2 steps, use a square. Another intermediate skill. Read percent change directly from the multiplier. We have the model. Value equals 300 times 0.92 to the power n. The question is, what percent change happens each step? Pause and try it. Then we'll explain the shortcut. The multiplier is 0.92. Because it's less than 1, this is decay. To find the percent decrease, compare it to 1. 1 minus 0.92 is 0.08. That means an 8% decrease each step. So you can read it instantly. Multiplier 0.92 means down 8% per step. Advanced practice. The key is converting time into steps. The culture starts at 200 and doubles every 3 hours. Find the amount after 12 hours. First convert 12 hours into the number of steps. How many 3-hour chunks fit into 12 hours? Pause and solve it, then we'll go through it. Every 3 hours is 1 step, and 12 hours is 4 of those steps. So n equals 4. Doubling means the multiplier is 2. Start is 200, so the model is 200 times 2 to the power 4. 2 to the 4th is 16. 200 times 16 is 3,200. This problem is a perfect SAT trap. If you forget to convert 12 hours into 4 steps, everything goes wrong. So always do the time step conversion first. That wraps up exponential models. Here's the big idea. Exponential change is percent change repeated over equal steps. So the multiplier tells the story. If it's greater than 1, you have growth. If it's between 0 and 1, you have decay. Before you calculate anything, pause and label the 3 pieces that control the whole model. The start value at n equals 0, the multiplier per step, and n, the number of steps. Once those are clear, the equation becomes automatic. Value equals start times multiplier to the power n. And one final SAT reminder. Your predictions are strongest inside the data range, not far beyond it. Great work. If you want to review, rewatch the practice section and focus on labeling start, multiplier, and n first.